So the shell structure uh, in building construction, just a thin curved plate. And so what the really unique aspect is that that plate is so thin that there's really no bending in it. So you end up with compression and tensile forces. Those are axial. So in the plate of the shell, and also shear stresses that act in the plane of the surface. So nothing really acting perpendicular to the shell itself. And just like you would, if you had a piece of paper and if you folded it into something that was ribbed. So here you would have something that really wouldn't, if you held both ends, it would have very little, it would have almost no rigidity to it. But if you folded it so its shape, the geometry is what changes the internal forces. So here's something that would be looking for bending stresses and basically having very little moment of inertia. So these have very little moment of inertia, but there's very little bending stress that shows up. And then obviously the other thing is that the weight of these structures is very small, but very challenging, but just elegant, elegant sort of structures, and you kind of get a feel for the connection points down there. And unless you think that these things never really exist in real life or close to us, this is the Santa Maria Airport. It says it right there. And so up here you've got a roof structure that's a shell. So you've got a curved shell. So this is akin to that piece of paper. And so that's what helps span that space. Instead of something that would be flat like that, you've got something that creates the ability to span based on its shape. So it's quite, you get a lot of geometry aspects to it. So very hard to build. Those are not the easiest things at all. A lot of cast in place, monolithically poured. I mean, this is actually pretty thick, compared to something that would be sitting here that has a little bit of cantilever to it. But sometimes I feel like I could look at those structures all day. Again, from a design point of view, we really don't have anything to do there. So we're kind of to what you would have on that project. So what we're going to do here is, you've got a lot of this is in that that handbook, right? The numbers, the sizing, and so this is in terms of large spans, sort of real big spans. If you look at that picture, like that's for scale, those are people standing right there. So this is extremely large, very, very heavy weight for one. And so you end up with extremely large cross sections, high weights. And so you can get them to span, quote, long, but that's why we put those limits on what we're generally trying to do. If you go beyond 50 feet, 40 to 50 feet, then they start to get pretty big, extremely big. I mean, these are very large spans. And this is, how close those beams would be spaced in the horizontal direction. So you would need one of those beams, every 25 feet, quote, on center. So that's what this refers to right here about located at columns. Generally, the reaction force is going to go right down into a column. Right. This is actually the girder right there. Those are beams that are framing into it. And so you've got your span to depth. And so just, this is between 12 and 15 from a minimum depth requirement from a sizing point of view. So another reason why this is important, not just for bending, but also for, we don't deal with it, but lateral stability. So the depth of that thing needs to be substantial enough so that it stays in plane. It doesn't fall out of plane. So with the depth, then that also assists in the width. So from concrete, you end up with, on large, again, this is for large spans, you would end up frequently post-tensioning. Just a second. Get that out of there. Right, it might be used very, very high, the weight we've talked about, and that's where you see the depth, the span to depth, and it's kind of like L/10, where the steel was kind of L/15. Still, from how close they need to be would be about 25 feet is how you would space those girders. That would be about the length. In between them, right, you would place your beams, which would go from, right, girder, I'll make a G right there, to girder. So still need to be able to span between those girders. Just like in your, on project one, you need to be able to span between, you know, if it's, you've got a couple trusses, you're going to need to span between those. All right, so open web steel joists versus engineered trusses. So we'll have some pictures here in just a second, but the open web steel joist, I mean, that's a repetitive used member. So it's something that's going to be closely spaced. You can get great span out of them. You know, you can get 100 feet, but you're going to need to have many of them. So on top, because they're so close to each other, right, there wouldn't be beams in between the joists, but you would have some sort of a deck. The decking material itself would span between the 5 to 10 feet. And so you end up with a depth requirement of about L/20. So you get something that's shallower, right, as opposed to an engineered truss. But it's going to be repetitive, it's economical, it's sort of off the shelf kind of catalog buying. Engineered trusses, which probably you'd end up with, again, either one would work. Either one would work in your project one. You could have both if you wanted. I mean, these would go in a little bit quicker. An engineered truss, I'm trying to get you guys to have that in there. And so you're spanning between columns, and you're going to have between them, right, between these engineered trusses, you're going to have maybe 25 feet, and between them, you're going to need your beams. Oh, shoot. Thank you. Just a minute. Somebody's looking to get in. Let me stop share here. Yeah, there she is. Thank you. Get back. All right. Chat is back. Okay. So between the trusses, right, if you had multiple trusses, which you most likely would, you would have some beams that would have to frame between them. And these are, custom. Those are designed, and that's why and I'll go over that, but that's why we end up designing what the depth is, and then also what the nodal distances are as well. So we'll see that here in just a second again. So on those engineered trusses, that the panel depth. So on those long span trusses, right, you should have a truss. You could do you could do the joist, but I would much rather have you do that. You've got dealing with long spans, right? You're gonna have to construct them, and they're not off the shelf. They're customized, right? We've got design aspects to them, so that's why you're going to have to end up, right, designing for a truss that would be simply supported, then you're going to need to design the top chord or the upper chord for compression. And so that ends up with some elements of, there's that pen doing that again, for buckling. And so it looks very similar, use a lot of the same column type of analysis to make sure that you've got something that is able to be a certain length without buckling and also taking the axial load. So if you, I'm gonna draw one here. It's just a square one, but we've seen trusses that have different sizes to them, and the reason why would be, that in the middle is where, if you think of that as a shear and a moment diagram, right? This is where the moment is the maximum. And then as you get closer to the ends, you get less and less moment. So that's why you can end up with trusses that they're going to have their greatest depth in the middle where the moment is most maximum. So here's a couple more here. You've got, this would be a repetitive use. Look at the open web steel joists, right, that are used at a certain spacing. Not the best, but we got a huge span here that we're able to get across. And so that's what has been used here, right? In between those is just decking. So that would be, again, like 5 to 10 foot spacing. And then there would be your span to depth ratio. Those engineered trusses, sometimes depending on the span, we may have curved chords, right? Could have something that has an arch to it. So sort of a combined system. So you can have something that's vaulted. That's kind of in the Cal Poly Rec Center. I'll have some Cal Poly pictures for us here in just a second. Right here, trusses need to be deepest at mid-span. We talked about that's where the moment is maximum. That would be why. And from a minimum depth, this is why if you've got a huge span, you're going to end up with a huge depth, right? You've got that L over 10. And so you just need to keep in mind that the story height, right, is going to tie to that. So on project one, when you've got an engineered truss, right, you're going to just probably end up having a higher ceiling. I shouldn't say that, floor height. It doesn't depend on, you can make the ceiling however you want, but in terms of floor to floor, if you've got something, you're going to end up with something that's pretty substantial from a depth point of view. And, from between those big trusses, right, make sure that you're going to have beams that are spacing. So those trusses are going to have to be, kind of see the spacing here. Let me see if I can get, well, there's one, there's one, there's one. So we've got some spacing on our engineered trusses as well. So to bring you back to Cal Poly, I wish we were here. Bring you back home, there would be the bookstore. So it's a Varandale truss, concrete. And so you see the big span. And so that's how they get across. And you see the depth. Just a second. Here we have a double shot here. I'll make this a little bigger. I don't know if you guys have seen this. So this would be a shot of the rec center. So you've got multiple trusses. Not only do we have beds in there for, hopefully that never get used, there would be some smaller trusses that are going to hold oxygen lines. But then up top, you see the large scale structure. So tried to bring you back a little bit to Cal Poly. There's some lateral system right here. See some lateral system that is present on the exterior, but right here, this would be the truss that's spanning all the way across that space. So sorry that we're not all there. We could go walk around to it. So this is what we'll do. So just to review, you've got a homework 1, right? I'm asking for it by 8. If there's a problem, if you're running into a problem, I know this is still just our first week of doing, second week of doing all this. So if you need an extension, just email me, please. Email me, please, after class. I can work with you. I've got a Dropbox. Several people have already done it. What I'm going to do is this. I am going to break you guys up. I can create breakout rooms, and I'm going to do it by your group. And you could stay a long time. You could stay a short time. It's completely up to you. I will not take offense either way. Let's see where we are here. I will not take offense either way as to what you want to do. But let's do this. Give me, if you'd like, give me about 5 minutes. It might take me a minute to do it. But I'm going to create breakout rooms. And so if you want to take a 5-minute break, go ahead. And at 4:55, you can come back, and you would be more than welcome to work with your group members. Specifically, if you want to go through where your long span structure is, where your truss is, and then also your where your what column line you might want to work on. Kristen, you have a question?
Right, yeah. I was wondering.
Slow here, sorry.
I wanted to make sure you received those and how to.
Can you say that one more time? I lost you halfway.
Sorry. Last time we met as a group, you asked for the floor plans for our
Yes.
building.
Yep.
I was just